All right, we're on to lecture number 6. So in lecture number 6, it's going to be divided up into two parts. So part A, this part, we're going to talk about temperature and heat. You might remember we talked about temperature a little bit in the 5th lecture, but I got a little bit more to tell you about temperature and heat. And then in part B, oh my God, sig figs. You thought we were done with sig figs. Well, I got one last thing to tell you about sig figs we're going to go over in part B. All right. So let's go and get started in part A. So you might remember in the 5th lecture, we talked about what temperature is, and specifically we spent some time talking about temperature scales. You got Mr. Fahrenheit scale, Mr. Celsius scale, and Mr. Kelvin scale, Lord Kelvin scale. So their temperature, again, measured in those units. Maybe I should write them down up here. Fahrenheit, Celsius, Kelvin. Now, in this lecture, we're also going to talk about heat. Now, heat and temperature are not the same thing. One way I can tell you that they're not the same thing is heat is defined as, has different units, I should say. Heat is measured in things like joules or calories. Those are units of heat. So they have different units, and that's because they're different ideas. So first off, let's define them. And then really what we're going to spend our time in this video is how these two things are related, okay? So temperature, I need to write it right here, is really a measure of the average energy, the average energy of the molecules in a substance. Heat, on the other hand, is a measure of the total energy of the molecules in a substance. The total energy of the molecules in a substance. So the big difference is the word average. And then the other word that's kind of different when we get to heat is total. So the average energy versus the total energy. So let's do a little example of what I mean by that. So let's say tonight you're going to cook some dinner, you're going to make some pasta, whatever, and so you get out your pan, and you have your little saucepan, and in there you put some water, and you warm that water up. You want to get it pretty hot to cook your spaghetti or whatever, so you get it up to 80 degrees Celsius. Now, let's compare that to the ocean, all right? The ocean, even when it's warm in the ocean, like if we think in terms of Celsius, like, I don't know, Fahrenheit, maybe it gets to like 60 or something, I don't know, out here in California. But, in Celsius, that might be like 15 degrees Celsius. So if we compare these two things, we've got a pan of water, and we're going to compare it to the ocean of water. They both have different temperatures, right? So one is 80 degrees and the other one's 15 degrees. So they're way different temperatures. So what that tells me is that on average, the molecules in the pan of water, they're moving way faster. So the higher the temperature is, every little molecule is bouncing around faster. When the temperature is lower, those molecules are moving slower. So if I kind of draw that out, let's say here's a little water molecule. So he's moving kind of slow, and there's another one moving kind of slow. Over here, they're moving way faster. They're going crazy, okay? So temperature kind of has to do with the speed the molecules are moving at. So on average, in the ocean, those molecules are moving slower. They have less energy, in other words. But in the pan of water, on average, they're moving way faster. Now, the difference is, when I get to heat, total, the word total. So yeah, in the ocean, every little molecule's going kind of slow. But if we add up all of their energies together, because there is so many of them, billions and billions of billions of them compared to a little pan of water, the total energy, even though they're kind of sluggish, the total energy of them all together is way bigger. So the ocean would have more heat, it would have higher heat, and the pan of water would be lower in heat. Well, I guess we'll write less heat, all right? So the difference is when we combine all those energies together in the ocean, you get a way bigger amount than if it's just in the pan. All right, so that's kind of the big difference. Now, what we're going to move on to next is the idea that these two things are related. So let's go to another slide where we'll talk about how they're related. All right, so let me go ahead and flip over to that. So how are they related? Well, they do affect each other, right? If you want to warm something up, if you want it to have a higher temperature, the way you do it is by adding heat to it. So there's going to be a little equation that relates these two ideas. Now, let's go ahead and let's kind of talk about it generally again. And so let's go with our example where we're warming up something in a pan. All right, so we get out our little pan and we put something in it, some water, some butter, some oil, whatever it is. And I want to know how much energy, how much heat does, I wrote the wrong letter there. Oh, let's erase that. Does it take to warm up the stuff in the pan? All right, so in that pan we put oil or water or whatever it is, and I want to think about how much energy is it going to take to warm it up. So that energy, right, would come from the stove. Like your stove is going to give me that energy. So how much work, how much energy does the stove need to do? Well, there's going to be several factors that matter. The energy I need to get from the stove, the heat, in other words, is going to have to do with, first off, how much stuff did I put in the pan? So the way I could talk about how much stuff did I put in the pan, that would be like the mass of stuff in the pan. Am I heating up 10 grams of stuff or 100 grams of stuff or 1,000 grams of stuff? The more stuff, the more energy you're going to need. All right. Now, what else would matter? Another factor that would matter is how much I want to warm it up. How hot do I want to get it? So a way of saying that is the change in temperature. The change in temperature. Am I trying to warm up the stuff in my pan from 10 degrees to 20 degrees or from 10 degrees to 100 degrees? So obviously, if you want to get it really hot, it's going to take more energy than if you're just trying to warm it up a little bit. All right, another factor. Another factor would be what it is. If you're trying to warm up water, water doesn't warm up at the same rate that oil warms up, or that, I don't know, butter warms up, or whatever it is. So what it is, what you're warming it up, what it is. All right. Now, that's not like a really official looking equation, is it? Because there's a couple things in there that I got to be able to kind of understand a little bit better. And the one that we really need to focus in on just a little bit more is, we know what mass is, right? We know what mass is. Mass is like grams. And change in temperature, that's going to be like Celsius. It goes up 10 Celsius or 50 Celsius. The one at the end is the one that could be a little confusing. What it is. So the way we talk about what it is we give everything in the universe a number that has to do with how easily you warm it up. So what it is, now we don't really need to say what it is. There's a better name for that. And that is called the specific heat. The specific heat. You might hear it called the specific heat capacity. And that is basically, let me define it right here. The amount of energy needed to warm up 1 gram of something 1 degree Celsius. 1 degree Celsius. So it takes into account that different things warm up at different rates. So let's go ahead and kind of write this equation like maybe a little more officially. And the way that we usually write it, we don't usually use like words, right? We like symbols. So some of these symbols don't make a whole lot of sense. Sorry about that. Nothing I can do about that. So heat. The symbol for heat is a Q. Why is it a Q? I don't know. It's a Q. The symbol for mass, that one actually makes sense, M. And then the change in temperature, temperature is T, and the way that we represent change is a triangle. That's the Greek letter delta. So this stands for change in temperature, delta T. Change, oh, it's kind of hard to read that. Let me erase it again. That stands for change in temperature. Change in temperature. And then we need to have a symbol for specific heat, the energy it takes to warm up something 1 degree. And the symbol for that, you will see different symbols. Usually you see a capital C or maybe a lowercase c. So we're going to use this equation in a couple examples in this video. So heat is related to temperature changes. How? Heat is equal to mass times the temperature change times the specific heat. All right, so we're going to be practicing using this equation in this video. All right, now let's go to the next slide, and I'm going to show you a little bit about this equation, and we'll do a little example. So if I flip over, the first thing I'm going to show you is that in this slide, you see a list of specific heats. So those lists are on the right-hand side. So on the right-hand side, it tells me how much energy it takes to get 1 gram of this stuff 1 degree hotter. So the thing that's the easiest to warm up actually is lead. To warm up lead, or gold, they're actually tied, you need 0.128 joules to get 1 gram of lead 1 degree hotter. On the other hand, what this chart is telling me, to warm up water 1 degree, 1 gram of water 1 degree, you've got to add 4 joules, J stands for joules in this chart, 4.184 joules of energy to get it 1 degree hotter. So every substance warms up at a different rate. Things at the bottom warm up slower. Things at the top warm up quicker. All right. Okay, with that in mind, let's do a little actual calculation where we try to figure out how much energy does it take to warm up, I guess in this case, it's going to be copper. Okay, so let's read this question. Let's see what we're asked here. How much heat, how much energy is needed to increase the temperature of 75.5 grams of copper from 21.5 Celsius to 42.8 Celsius? So how much energy is needed to take 75.5 grams of copper and warm it up from 21.5 degrees to 42.8 degrees? All right. So let me go ahead and, well, it's a problem involving heat. They want me to know heat. So the way I would work it out is this equation. Well, I guess I'll just use the symbols, right? Heat equals mass times change in temperature times specific heat. All right, so we learned an equation in the previous set of videos for density. This is the equation for heat. These are like the only 2 equations we're going to see for a long time, all right? So we're going to practice using it, though, a little bit. All right, how much heat? Oh, I am solving for Q. How much heat is needed to increase the temperature of 75.5 grams? Where would that go? It goes in for the mass. So it would be 75.5 grams times the change in temperature. So now the change in temperature is not 21.5 and it's not 42.8. If I want to know the change in temperature, I need to subtract those 2 numbers. So this thing is starting off at 21.5 and I want to get it up to 42.8. That means, oh, maybe I should do it like a little scratch work right here. I am trying to get this thing, oh, if I work it out, 21.3 degrees hotter. So I would put in for my delta T, I'll try to be good with the colors here. Oh, there we go, 21.3 degrees Celsius. All right, so we got the grams, we got the Celsius. So the only other number we need is specific heat. So the specific heat of copper, it's in the question. I could even find it in the table if I didn't have it. So the specific heat of copper would be 0.385. And you notice there's some crazy units on these numbers. There's joules over gram Celsius. Those are the units on specific heat. Joules on the top, grams and Celsius on the bottom. Now, you'll see them at the top of the table as well, like right here, right? Those are the units. All right, so at this point, we're in pretty good shape. All I'm going to need to do is I'm going to need to multiply these numbers together. So if I do 75.5 grams and I multiply it times 21.3 and multiply it times 0.385, the amount of energy it would take, well, if you work it out, oh, let me check my notes. It should give you 619. And again, oh, there's got to be units. 619. Well, let's see how the units work. Grams are here. Grams are here. Goodbye. On top and on bottom, you cancel. Celsius is here. Celsius here. Goodbye. You cancel. So the unit I'm left with is joules. So that sounds right. Heat is measured in joules. Maybe calories, but in this problem, it's joules. All right, with that, let me show you one more. Let me show you one more along these lines. All right, so let me take a little pause here and flip over to one more slide on heat and temperature. All right, let's try one more having to do with heat. All right, so let's see. It says a piece of gold has a mass of 75.8 grams. If I add 455 joules of heat to it, how much will the temperature of the gold increase? All right. So another problem with heat, if there's a problem with heat, you're going to be using this equation. There's only one equation. There's only one equation to know. This is the one you got to use. Heat equals mass times change in temperature times specific heat. So let's read what they give us and let's see what we're going to solve for. Hopefully we can get it done using this one equation. All right. A piece of gold has a mass of 75.8 grams. Oh, okay. They gave us M. If I add 455 joules of heat, okay, that goes in for Q, 455 joules of heat, how much will the temperature of the gold increase? So how much hotter is this piece of gold going to get? So I'm solving for delta T. I'm solving for delta T. All right, they do tell us one other number. The specific heat of gold is... And what's specific heat in this equation? It's C, so that goes in right here, 0.128 joules per gram Celsius. All right, so the specific heat is C. All right, so I'm kind of in pretty good shape, right? I got 3 out of the 4 things. I got to solve for the one I'm missing. I'm solving for temperature, but I got everything else. So the only other thing I need to do to be able to solve is I'm going to plug those numbers in that I have. This time, I think I'm going to have to do a little rearranging, though, because delta T is not by itself. So we're going to have to move some stuff around to get it by itself. But let's go ahead and get started by putting in the numbers we need. So for Q is heat. All right, 455 joules equals mass. Oh, yeah. Okay, I see that. 75.8 grams times change in temperature. Okay, that's what I'm looking for. How much will the temperature of the gold increase? Solving for delta T. All right, and C I also have 0.128 joules per gram Celsius. All right, so at this point, we're in pretty good shape, but we got to get delta T by itself. So the way I'm going to get delta T by itself, just like whenever we convert or anything, you need to take your numbers that are next to what you're solving for, and you got to move them to the other side. And the way you do that is if they're on top, you put them on bottom. You cancel them out. Another way of saying that is I got to divide by them. So I'm going to take both sides, and I'm going to divide by 75.8. Oh, because that'll make the 75.8 cancel. And I also need to divide by the 0.128. That'll make the 0.128 cancel. All right, so to work it out, I'm going to go ahead and get these things to cancel. But if I do that on the right, though, when I'm canceling, that means I also have to do the same thing on the left. So I'll divide by 75.8 and 0.128. Now, oh, that's a J right there. Sorry. All right. So, oh, on the right. Oh yeah, those cancel out. Beautiful. That's what we need. And then we'll have delta t is what I'm solving for, all alone on the right. I might be saying left and right backwards sometimes. I'm sorry about that. I'm getting too excited, I guess. But yeah, it's going to be alone on the right. And then you'll have this on the left, 455 joules. And then 75. Oop, I wrote the wrong number here. Shoot, let me fix that. 75.8. And also on the right, left, 0.128 joules per gram Celsius. All right, so now you got to get this in your calculator. So the way you'd get this in your calculator, make sure you do this the way I'm about to tell you, or else you're going to get a math mistake on your hands. You would type in 455 joules. And then the way I would recommend doing this, there's more than one way, but the way I'd recommend doing this is to 455 joules divide by this number, 75.8. And then the next number is on the bottom, the 0.128. So you're also dividing by it. So divide again to hit the division key a second time. You're going to divide by 0.128. So it's 455, divide by 75.8, also divide by 0.128. If a number's on bottom, you're dividing by it. So you should be hitting the division key twice. If you work it out correctly and you get the right answer, what's the right answer going to be? It should be 46.9 Celsius. That's rounded correctly and everything. Okay, so hopefully it isn't too bad. You know, it's a lot of math right now, so you know, you have to get used to doing some calculations. When we do our Zoom, we'll do a little more practice on this just to make sure you feel okay about it. All right, so that's it for this video. So there'll be one more part to this, one part B, on a totally different topic. So we'll move on to that in just a minute. But for this part, oh yeah, heat and temperature, we're done with that for now. I'll see you next time.